Hello everyone, welcome back. Imagine your AI agent already answers this question. Plan a 5-day Dubai trip from Chennai. A few seconds later, another user asks, create a Dubai itinerary for 5 days, departing from Chennai. Different words, but same intent. Your system treats these as two completely new requests. The agent broker calls the LLM again, consumes more tokens, adds more latency. And you pay twice for nearly the same answer. Now multiply that across thousands of users. This is the exact problem semantic caching solves. Let's start with traditional caching. The first time a prompt reaches the system, the cache checks for an exact key. If the prompt is not present, it is a cache miss. The request goes to the LLM, the response is generated, and the prompt response pair is stored. If the exact same prompt arrives again, it becomes a cache hit. The stored response is returned without calling the LLM. This is fast and inexpensive, but also extremely literal. Change one word, add punctuation, or rearrange the sentence, and the cache may no longer recognize it. Human language does not repeat itself like an API request. We express the same intention in hundreds of different ways. That is why agentic applications need semantic caching. Instead of comparing text character by character, semantic caching compares meaning. The incoming prompt is passed through an embedding model, which converts the text into a numerical vector, a mathematical representation of its meaning. Previously cached prompts are stored as vectors as well. The system then performs a vector similarity search, commonly using cosine similarity, to find the closest cached request. If the similarity score crosses a carefully selected threshold, the system treats it as a semantic cache hit and returns the previous response. If no sufficiently similar request exists, it becomes a cache miss. The request continues to the LLM, and the new prompt, vector, response, and metadata are stored for future use. The threshold is not a universal number like 0.9. It must be tested and tuned for your specific business domain. In a MuleSoft Agent Fabric network, the agent broker coordinates LLMs, agents, and MCP tools. Semantic caching should sit on the expensive LLM invocation path, after identity and safety checks, but before the request reaches the model. A production design can use 3 levels. First, an eligibility gate decides whether the request is safe to cache. Second, an exact cache performs a fast hash lookup. Third, only if that fails, the semantic cache performs an embedding and vector search. On a semantic hit, the stored response is returned. On a miss, the request continues through the governed LLM proxy on Omni gateway to the model provider. The generated response is then stored with its context, version, and expiration time. This hybrid design gives us the speed of exact caching and the flexibility of semantic matching. But semantic similarity does not guarantee business equivalence. Consider these two prompts. Recommend a laptop under $1,000. Recommend a laptop under $3,000. The vectors may be extremely close because most of the language is identical, but the budget changes the answer completely. The same applies to travel dates, passenger counts, user roles, currencies, locations, account balances, and access permissions. That is why important constraints must be extracted and compared exactly before accepting a semantic match. The cache must also be isolated by tenant, user permissions, language, system prompt version, model configuration, and knowledge base version. Otherwise, a response generated for one customer could be exposed to another. And never cache state-changing operations. Searching general travel guidance might be cacheable. Creating a flight hold, making a payment, canceling an order, or updating a customer record must always execute through the relevant MCP tool. An agent should reuse knowledge, not replay actions. Don't forget to subscribe Mule Ace Academy for more such insights on MuleSoft and Agentic AI. Thanks for watching.